In this talk, I'm going to give a very high-level idea of our paper, Machine Checking Multi-Round Proofs of Shuffle, Terelius-Wikstrom, and Bayer-Groth. And Terelius-Wikstrom is used in Norway and Estonian election to a public office, and Bayer-Groth is used in Switzerland and Australia. And this is a joint work with Thomas Haines from Australian National University and Rajeev Gore from Polish Academy of Sciences. So let's get started. What is a shuffle? Well, it's a computer program that takes a list of input ciphertext and produces a list of output ciphertext. And the idea is to break the link between output and input. So if you pick here any V, you should not be able to figure out it's coming from which U. And how does a mixnet do this? So internally, it generates a secret permutation, permutes the input, re-encrypts those inputs and output it. And these primitives are extensively used in election. And you can think on your left that ballots are coming from a voting booth, and to your right going to bulletin board or next mix servers. However, there is a catch. If your server is malicious, it can drop few of its inputs and produce completely manufactured artificial values. And if that's your ballot, then it's very dangerous. So in addition, they produce a zero knowledge proof, which you can think of as a data that attests the fact that underlying plain text in the output ciphertext is the same as the underlying plain text in the input ciphertext, modulo some permutation. Now there's a key question. Why should we care about these primitives? And in my case, and hopefully in your case as well, we care about democracy. At this security conference, we know that constructing a secure system is very difficult. And in the past, many voting companies have screwed up with the simple zero knowledge proof, and trusting them with the mixnet is probably a suicide. So, and I have nothing against Switzerland. You hold me, don't hold me, I have nothing against Switzerland because the phenomena is same worldwide. Either it's Russia, here United States, Australia, my very own country, India, where people are talking about replacing EVMs with paper ballot. So I hope at this point you are convinced that software bugs are a major threat to our democracy. So let's see how softwares are written to protect our democracy. So this is a Bayer-Groth source code written in Java by a company called Swisspost, which basically handles all the electronic voting software in Switzerland. And Bayer-Groth has very nice property, completeness, security property, completeness, soundness, and zero knowledge. And what does this mean is not super important in context of this talk. The part is, it's security property of Bayer-Groth, but we cannot establish this for our Java or for the Swisspost Java implementation, because Java is not a sound language, and we cannot express any formal, we cannot get any formal guarantee about Java implementation. So what we did, we took the algorithm and wrote it in a Koch theorem prover. And Koch theorem prover is developed by a French research agency, INRIA. And you can think of it like a programming environment where you write your definitions, and then you write your spec in the same language, and then prove it, and then write tactics, crunch it, and prove it. The best part of this whole deal is that it's a constructive. So you can get an OCaml out of this Koch formalization that runs on a machine. So any French taxpayer, just a side note in this audience, thank you for your taxes to fund this Koch research. So this is what I was saying. On contrary to Java implementation, from Koch we proved that our Bayer-Groth implementation has completeness, soundness, and zero knowledge. Then we extract a code out of it, and we run that code on a machine. And that code is as good as Swisspost's Java implementation. Now, given that we have invested 2 years in this project, how can Swisspost take advantage of our work? There are 2 ways. In one, they can literally replace their Java code with our OCaml code. I believe that's going to be very difficult for them. It will create more problems for them than for us, and they don't want to do this. So there is another way they can do this. They can take their Java code, execute it, and from that execution, they get some trace. They can feed that trace to our OCaml code, and if our OCaml code says yes, then they know that that particular execution has no bug. But if it says no, then that particular execution has bug. And again, I am trusting in this whole process, the Coq extraction and OCaml compiler. But there are projects happening in Coq community, for example, MetaCoq, through which we can compile, get a verified assembly code all the way up to machine level. But it's in the process. And this is more intended use, verified verifiers for software independence. And I want to talk about verified verifiers to achieve software independence. So software independence was proposed by Ron Rivest to protect elections from any kind of mishaps happening due to software. So Ron Rivest said, a voting system is software independent if an undetected change or error in its software cannot cause an undetectable change or error in an election outcome. So what we basically do is when we conduct electronic voting, we collect a lot of data. We log every step, and once the election finishes, we check it. But sometimes that check itself requires to run a software because it's tedious to do by hand. So you need to write a software. So software independence is a nice property, but then you again need to write a software. So now we are in the same situation. So there is this very nice idea of verified verifiers, that you write your verifier in some formal language like Coq, and then you extract a code out of it, and then you run that code to test that whole log if it's right, if it's in the right shape or not. So what are our contributions? We have, so far, all the previous work is formalized is 3 rounds. So in this project, we formalized more rounds, 5 and 7 rounds. We also clarified a claim about Terelius-Wikstrom. And so it's claimed that it's a proof, but we figured out, no, it's not a proof, but an argument system. And finally, this is the first formally verified implementation of Bayer-Groth. And the best part is it's usable. So here is how it looks. You run. It takes the data. That is the trace generated by Java from Swisspost. And it says true. And that true is important. If it says false, then you need to go and check what's wrong with the Java implementation. And now I'm happy to take questions. You can take our Coq formalization and run it. Thank you very much.